Type almost anything into Google. A question, a name, half a song lyric you can't quite remember. 2.8 billion results. Found and ranked in less than half a second. Now here's the part nobody stops to think about. There are over 100 billion web pages out there. If a computer checked them one at a time, page 1, page 2, page 3. Even at 1 billion checks per second, some searches would take minutes. You'd be staring at a loading spinner long enough to make a sandwich. So it doesn't do that, nothing fast does that. The secret isn't a faster computer, it's a smarter strategy. One so powerful it can find a name among 8 billion people in about 33 steps. 33, not 33 million, 33. By the end of this video, you'll understand that strategy completely. You'll see why one approach crawls while the other flies. And once you see it, you'll notice it everywhere. Let's begin with a game. I'm thinking of a number between 1 and 100. Your job is to guess it. Every guess I'll tell you one of 3 things: too high, too low, or correct. Now, how would most people play? They'd start at 1, is it 1? No, is it 2? No, 3, no. If my number were 99, you'd be guessing for a very long time. In the worst case, 100 guesses, that's the slow way. But you're smarter than that. Watch what a clever player does. Their first guess, 50, right in the middle. And I say too low. With one guess, you didn't eliminate one number, you eliminated 50. Everything from 1 to 50 is gone, instantly. Now do it again. The middle of 51 to 100 is 75. Too high, everything above 75 vanishes. 2 guesses in, 100 possibilities crushed down to 24. Keep halving, 62, too high, 56, too low. 59, too high, 57, correct. 6 guesses, that's it. No matter which number I picked, you'd find it in 7 guesses or fewer. Out of 100 possibilities, every single time. That clever halving strategy has a name. It's called binary search. The slow, one-at-a-time approach is called linear search. The rest of this video is about the staggering gap between those two, and why that gap makes the modern internet feel instant. Let's define our slow friend properly. It's not a bad algorithm, it's the honest one that makes no assumptions. Linear search means, start at the beginning, check each item one by one, until you find what you want, or reach the end and conclude it isn't there. Imagine a row of lockers, and you want the one holding a red envelope. You don't have a map, so you open the first locker, nothing. The second, nothing. The third, there it is. 3 checks, not bad, but that was luck near the front. What if it's in the last locker? Now you check every single one. And if it's not there at all, you still check everyone just to be sure. That's the worst case, and it's the case we plan for. With linear search, the work grows in direct proportion to the size of the list. 10 items up to 10 checks, 1,000 items up to 1,000 checks, 1,000,000 items up to 1,000,000 checks. Double the list and you double the work. This is what we call O of n linear time, the straight line. Honest, predictable, and for big data, brutal. Let me show you the actual logic, written as plain code. For each index from the start, look at the item. If it equals the target, return where you found it. If the loop finishes with no match, return -1, not found. 5 lines, anyone can write it, and that's its charm. Linear search has 2 real superpowers. First, it works on anything, shuffled, chaotic, any order at all. Second, it needs no setup. You can search the instant the data arrives. So why isn't it enough? One word, scale. When n is 10, who cares? When n is 10 billion, it's a death sentence. And the digital world runs on lists far bigger than 10 billion. Which brings us to the contender. Binary search keeps 3 ideas in its head. The low end, the high end, and the middle. Every step it checks the middle and asks, is my target higher or lower? If the target is higher, the answer is in the top half. Move low up. If it's lower, the answer's in the bottom half. Move high down. Either way, you just deleted half of everything left. Then find the new middle and repeat. Watch the dead space pile up. Every comparison shaves off half of all remaining candidates. That compounding is the entire trick. Linear search subtracts, binary search divides. Here's binary search as code. A little longer, but every piece you just watched. Low starts at the front, high at the back. While there's a range to search, find the middle. If the middle is the target, done. If the middle is too small, throw away the bottom. Low jumps up. If the middle is too big, throw away the top. High drops down. When low and high cross, the range is empty and the item wasn't there. But there's a price of admission. Binary search only works if the data is sorted. The whole strategy depends on higher or lower actually meaning something. In a sorted list, higher points to one half, lower to the other. In a shuffled list, the middle tells you nothing. The magic evaporates. So binary search makes a trade. Order up front for blinding speed after. That sorting is what buys 4 flips instead of 1,000. Remember that trade, we'll cash it in later. Now for the payoff, real numbers on both. And the gap is bigger than your intuition expects. Linear search worst case takes up to n steps, 1 per item. Binary search takes the number of times you can cut n in half. That operation has a name, the logarithm base 2, log n. And it grows almost unbelievably slowly. Let's compute it, a list of 8 items. Halve 8 4, halve 4 2, halve 2 1, 3 cuts. 3 steps where linear needs 8. Nice, not jaw-dropping. Keep watching, this is where it accelerates away from you. 1,000 items, linear 1,000, binary 10. 1,000,000 items, linear 1,000,000, binary 20. To search 1,000,000 things, you look at 20. 1,000,000,000 items, linear 1,000,000,000, binary 30. 8 billion people sorted by name, linear 8 billion, binary 33. That's the number from the very first frame. Now you know where it comes from. Here's the single most beautiful fact in all of this. Every time you double the list, you add only one more step. 1,000,000 to 2,000,000 items, and binary needs one more comparison. 20 becomes 21, double again 22. You could double until the list has more items than atoms in your body. And still add only a handful of steps. Linear search, meanwhile, would double its work every single time. This is the picture worth memorizing. The straight red line is linear time, climbing forever. The flat blue curve is logarithmic time. It barely notices the data growing. That flat curve is the shape of instant. Linear asks, how big is the list? Binary asks, how many times can I halve it? And halving is so violent that even astronomical lists fall in a few dozen blows. That is the power, everything else is detail. Talk is cheap, let's race them. Same list, 1,024 items sorted. Same target, hiding near the end at position 1,000. On your marks and they're off. Linear starts its long march, 1 2 3 4. Binary makes its first cut at 512, too low. And half the list is already dead. Binary's second cut 768, third 896. It's closing in by hundreds at a time. Look at the counters, binary is at step 7. And linear hasn't even reached the halfway mark. Done, binary search found it in 10 steps. And linear search, still going, 412. It'll get there 1,000 steps later. Binary finished, refilled its coffee and watched. And remember, this was a small list, just 1,000 items. Scale it to 1 billion and linear isn't slower, it's impossible. The gap doesn't grow, it explodes. Time for the honest answer to the title. Does Google literally run a binary search over the whole internet? No. The reality is even cooler, and binary search's principle sits at its heart. When you search best running shoes, Google doesn't scan billions of pages then. Long before you typed anything, it built an inverted index. A colossal sorted dictionary. For every word on the web, a ready-made list of which pages contain it. So the question becomes, look up the word running in my sorted dictionary. Looking up one key in a sorted structure of billions. That is exactly the problem binary search was born to solve. The real databases use structures called B trees and hash tables. And a B tree is, at its soul, binary search's bigger cousin. Same idea, don't look at everything, keep dividing the space. Then Google does this across thousands of computers and ranks with PageRank. Layers upon layers of cleverness. But peel them back and you find the same humble insight. Don't check everything, halve the problem again and again. That's why the title is fair, binary search is the spark plug. The idea of divide and conquer that makes giant search possible at all. Without it, there's no instant internet, just a spinner and a sandwich. Let's lock it in. Linear search, start to finish, one at a time. Works on anything, needs no setup, but its work grows with the data. O of n. Binary search, halve. Demands sorted data, but finds a needle in billions in a few dozen steps. O of log n. The one idea to carry with you. Linear search subtracts, binary search divides. And repeated division is one of the most powerful forces in computing. It's why your phone search is instant, why databases scale. Why 8 billion people collapse into 33 steps. A guessing game and the world's biggest search engine, running on the same idea. Once you see it, you can't unsee it. That's the power of binary search. There's a natural next question. How does the data get sorted in the first place? That's a whole beautiful world of its own, and it's where I'll take you next. If this clicked subscribe. Next, the surprising magic of sorting algorithms.